decision trees, which are very popular technique in machine learning. Decision trees used to be used a lot in, I don't know, 2 decades ago, 3 decades ago. But they sort of fell out of fashion because they don't tend to generalize very well. And they have some very nice properties which will become clear as we go through this lecture. But because of their inability to be very good at predicting, folks stopped using them. But then what came along was an idea of essentially that exploits what you did for your last homework, which was the bias variance trade-off, where even though trees have very high variance in their predictions, if you take many trees and you average them, you can get rid of the variance. So on Thursday, I will make this a bit more clear. And the advantage of being able to do this is that it becomes possible to take trees and build some of the most powerful classifiers that we know of. Things like random forests, also known as decision forests, and boosting. To give you some perspective, those face in your cameras, most of you have iPhones and so on that detect faces. That is the result of running one of these techniques. Or if you play with the Kinect, how many of you play with the Kinect? Okay, that's also one of these techniques, deciding where your hand is and where. And so on Thursday, I'm going to go over these applications. Or if you wanted to classify 1 billion web pages, you could use random forests. Okay? So you can do lots of things with these techniques. But in order to understand what a forest is, we first need to understand the tree. And so today I will focus on just the simple decision trees. So in particular, I'll cover decision trees. I'll discuss how the concept of entropy is used to build the trees, and hence the reason why I asked you to do an entropy question for your last homework, because we will use that result today. And finally, how we use trees for classification. Okay, as I said, you've seen these. Let me adjust the lights. You've seen these detections of faces with your cameras, and that's basically built with the techniques that we're going to cover. But just like you use them to detect faces, you could use them to detect anything. In this case, you could use them to detect, as in these pictures, to detect pedestrians. And that would be essential if you wanted to build automatic driving cars. And for those of you who haven't seen the Kinect, that's pretty much what it is. So it's essentially this device that's over here. Actually, I don't know. Is this the Kinect? For those of you who play with it. This guy. There you go. I've held one of these. I used it to track rats here in the neuroscience lab once. It didn't work very well because the sensor was designed for a particular scale. So essentially what it is, it's a sensor that projects an infrared grid on you. So even if it's dark, it works. And so what it does, it extracts a sort of a depth image. And then where the random forests come in is a classifier that lets you predict whether something is a hand or a shoulder or an arm, etc. So on Thursday, I'll go over the details. But what this enables you is to have something that's completely wireless. So you put the device there. The device projects a grid on these two folks here. And then basically now they're immersed in this game. So these characters here in the game on TV have exactly the same poses that they have. Okay, so you can do swordsmanship just by going like this without any wires. You don't need the Wii or anything like that. I think the Kinect holds a record, if you go to the Wikipedia page, for one of the highest sold consumer electronics after its release. So even though this is just like a game, we're talking about billions of dollars involved in this, and the sort of the fate of a company, essentially. Okay, how does this work? So a decision tree essentially is a structure that will split data points, that will categorize data points into different bins. So let's assume that my data consists of this. 5 cases. Okay, so I have 5 data points, 2 that are of the positive class and 3 that are of the negative class. Okay, so for example, I might be measuring a height and weight, and then one class is I'm saying whether you're fat, and another class whether you're thin. Okay, so I'm trying to have an automatic classifier that looks at people's height and weight and can predict whether they're fat or thin. So we have 2 classes. We have 5 individuals in this case. And so what a decision tree does is, well, it's a tree, as this picture shows. And we start with a root node. And as we go down the tree, the first thing that happens is in the root node, you have access to 5 cases, and then you apply a decision. So the decision could be something like, is the height above 2 meters? So only one individual has height greater than 2 meters, and so that individual goes this way. All other individuals are less than 2 meters in height, and they go this way. And then I apply another decision. Is the weight above 200 kilos? If the weight is above 200 kilos, then some individuals go this way and some individuals go the other way. So if you're short and you weigh more than 200 kilos, you probably go in one direction, and if you're tall, you go in the other direction. And you keep applying these decisions until you get down. And we will talk today about how we construct such a tree, just from data. But assuming that you had a tree, this is what you would do. You would move, you would be splitting the cases, and then some leaves would be empty, like these leaves. But for the leaves that have cases of one class, you would know that if an individual, if you had a new point that you don't know whether it's green or red, so a test point, so this would be the train data. If you now have a test data, then you would just do these decisions, and if the test data ends up here, then you know that it's red. Okay? And if it ends up in a green leaf, you assign to it the class green, and so on. So you assign to the point the class of the color that contains it. So here's another example where you have an image as input, and then you can check, your question might be, is the top of the image blue? If it's yes, then you ask the next question, is the bottom part of the image blue? If it's not, the image goes this way, and eventually it arrives at a leaf. And all the images that are outdoor scenes are likely to arrive at that leaf following these decisions. Okay? Of course, that's not going to be perfect because there's some stochasticity here. Okay.
So every level of the question being asked depends on which node you're at?
That's correct. So to each node, there is a question. So a node in this case is just a question that decides to split you left or right. In this case, it's a binary tree, so every time an individual comes in, that node makes a decision. And then the individuals that go to the right encounter a different node as they go down, and then again a new decision gets made about those individuals. So essentially what we do is we take the training, we will use the training data to construct this tree, but once we've constructed a tree, in order to reach a decision, you just follow these questions. And then when you get to the end, the class that you get, that is green or red in this case, will be what your neighbors are in that leaf. So if everyone in that leaf is red, then you get that class. In particular, for each you can think of a histogram here where you would have 3 out of 5 red cases, and where you would have 2 out of 5 cases. So to each node, in fact, there is associated such a histogram, because you can always just count how many are green out of all the number of points there, and how many are red. And so after that decision is made, once we reach this node here, the second node, we have half green and half red. So in this case, we have a half, or 2 out of 4. And as we proceed here, we will have 1. Okay. So if you happen to be a point in this leaf, if you happen to be any point in this leaf and you do not know your color, then what I can say about you is that you are 3/5 probability red. And that if you go to the left, then you are 100% red. If you go to the right, you are 50% red, 50% green. If you keep going to the right, then you become 100% red. Okay, so that's essentially what the tree is saying.
So this example, what's red and what's green?
Right, so let's make this more concrete. So we could have a data set that looks like this, where we have, so this would be our data. You would have 5 points, x1, x2, x3, x4, and x5. Okay, and then for each case, what you would have is really a vector that says what is the weight and what is the height. And so for x1, it might be that you know that, I don't know, these are 2 and 3.6, whatever the units are, 5 and 5.6, and so on. So to each x, there are sort of 2 coordinates. One that tells you, say, the weight of the person, or the weight of the rat, and the height of the rat. And then you also have a corresponding label. And that label, I'm going to denote y1 and y2, y3, y4, y5. And that label just says what class you belong to. So in this case, there are 2 guys that are green, and 2 guys that are, and 3 guys that are red. So you could think, for example, if one class could be cancer, and one class could be not cancer. And this could be the level of the level at which, I don't know, two genes might be manifesting themselves. Okay, so let's assume that you build a microarray and you look at 2 genes and you just check how much those genes are present in a particular individual. And so that's the input data, and then the output data is whether that individual has cancer or not cancer. Another example could be if those 2 numbers could represent, for example, the number of rooms in a house and the price that it was sold by the first time that it was built. And then the label could be whether the house is expensive or not expensive. Does that clarify? And so that's what we have here. We have 5 data cases. And the diagram I'm just showing that if you had 5 data cases and you're training data, and assuming that you have already built a tree. I have not told you how you build this tree, where these questions come from. That's what this lecture is going to be about. But let's assume that we had a tree, and let's assume that we had these 5 training data points. Then essentially, by following the tree, what the tree is doing is binning all these 5 individuals into different groups. Such that in some bins, the probability that you're red is 100%, and in some bins, the probability that you're green is 100%. Therefore, if you now put in a new person for which you do not know whether they have cancer or not, but you do have the level of excitation of those 2 genes, then you would just follow for that person the questions in the tree. And if the person were to end, for example, at node 14 here, then you would know that that person has to be red. Okay, because you would just based on the samples that everyone that ended up here was red. So based on the sample statistics, you should be red, based on the training data. Of course, with 5 data points, this is going to be a very noisy decision. But you, again, would realize that as you get more and more and more data, such decisions will get a lot better. Okay, so that's basically, go ahead.
I was just wondering, when we're going through this tree, do the points get sorted 100% one way and 100% the other way? Or can there be some probability of like a fraction going in one way and a fraction going in the other?
Good question. So the next slide will answer that. So here's another example of exactly the same thing. In this case, instead of just having green and red, I have now 4 colors. So multi-class classification. You now are yellow, red, blue, or green. So you could be 4 classes. And now, initially, if we look at this whole box, okay, this whole box is basically the root of the tree. There are an equal, so this is important to get. In this box, there is an equal number of green points and red points and blue points. And because the numbers of each color are the same, the root node here happens to have a histogram that has the same height for the 4 colors. Okay, that's because there's the same number. Those heights, they just counts, relative counts of how many green points there are divided by the total number of points. The points that have a color are the training data. The points that don't have a color, or in this case they are gray, these are test data. Okay. Now, if your tree has already been built, what we're doing essentially as we're going down these leaves is we're getting different histograms for the points. And in the previous case, it was clear that if a point ended up somewhere, it was definitely green or definitely red. In this case, if an individual, if you take one of these gray guys and you propagate that gray guy, and that gray guy keeps going this way when you ask the questions, and the gray guy ends up here, then all you can say is that that gray guy is most likely a red. Or in fact, you can say what the probability of the gray guy being red is, which is in this case would be something like 0.8. But that gray guy still would have a small probability, I don't know, 0.1 of being yellow, 0.08 of being green, and 0.02 of being blue. Okay, the height of those bars must sum to 1 because it's a probability. And it's the probability of it being of a class 1, class 2, class 3, and class 4. So it's the probability of the class given the data point V. And in this case, V is just a point in 2D space. There was a question?
Can you say anything about the point if it ends up in a non-labeled piece? Or
Sorry, if it,
Because you said there are some leaves that don't have any probabilities assigned to them.
yeah. So if a point were to end there, you would not be able to assign it a label. Because you just have no data. Okay, this will work as long as there is data at the leaves. And we will, when we build the trees, we will build them only as far as there's still data. We wouldn't keep building them to the point where there wouldn't be data in practice. Okay, so that's essentially a decision tree. So, and the nice thing is if we had such a decision tree, it will be very easy to look at it and see how the decisions are being made. So you would understand why a point ends in one leaf or the other leaf, because you can actually go and read the questions that are being asked. So let's look at an example of that. So here is something that was built for this company for customers. And so this decision tree basically has individuals. And then for this company, the first thing that they check is whether the total number of purchases of the customer is greater than $61,000 or less than that. If this customer has spent less than $61,000, then most likely this customer is a non-buyer. And if you know that the customer is a non-buyer, that's fantastic, because you don't need to waste your time advertising to that customer or inviting that customer to your, I don't know, wine and cheese. If, however, that customer has made purchases higher than that value, you then check how often does the customer do it. So the customer spends a lot of money and spends that money often, and the customer often does exorbitant spending, and I have no idea what this means. But eventually, if your customer is like a spendthrift, then you invite your customer to, then you invite this targeted customer to your wine and cheese and try to sell the latest, I don't know, condo downtown. Okay, so again, here's an example of a tree that has already been learned from data. We still have not talked about how we learn such trees. Okay, let's now move closer to how we would learn a tree. Now we're going to build, in short, we will learn the trees in a recursive fashion, and in a greedy fashion. So we'll learn the root node, and then we'll proceed to the next layer. And we can do this. Now it depends on different implementations. Some people like to go breadth first. Some people don't mind going depth first, up to a depth of say 5. There's a lot of different implementation details, but let's assume we're going breadth first. So you build the first one, next you build the second level of the tree, and so on. So the first question would be, how do you build the root? Now let's first look at our data set, and this data set comes from the artificial intelligence book of Stuart Russell and Peter Norvig. These are this is probably the best book in AI out there. Strongly recommend it if you are interested in AI and even in machine learning. It has some very good, it has an excellent introduction to machine learning. Okay, so in this example, there are 12 customers, 12 potential customers for a restaurant. Okay, and a restaurant might just be trying to decide how to run its operation to maximize the number of customers that it can get in the business. And so the restaurant is also trying to understand what makes customers spend money, wait in line or not wait in line. Because they want to be able to change their operations to ensure that they get the most customers. Obviously, they can't be super nice because they will lose money, but they also can't be completely awful and just turn everyone away because they will lose money that way too. So they need to find the right compromises to ensure that there's a reasonable queue outside and to ensure that they don't lose people. Okay, so In this data set, each of these x's is one customer. Okay? Each x is one customer, so we have 12 customers. For each customer, I record, this is a training data set, so these points are labeled. For each customer, we will record several attributes of the customer, and then we will observe whether the customer waited or didn't wait. The wait, didn't wait is the decision, i.e. the label. Okay? And in this particular data set, we have 12 customers, x1, all the way up to x6, and so on. And the 6 of these customers waited, and 6 of these customers didn't wait. And so each color point there corresponds to one of these cases. So this guy waited, and this one, and this one. x1 waited, x3, x4, x6, and these other guys. Okay? The other guys didn't wait, so the false means that they didn't wait, so I'm using a color to indicate false. Okay, so those are the 12 points these points here, these are the 12 points that I have here. Each point is a customer. Now before, I had the points being vectors in 2D. Now they're no longer vectors in 2D, they're vectors in a higher dimension. The number of dimensions is the number of attributes that we have here. So the inputs in this case are things like, are there any alternate restaurants nearby? Does the restaurant have a bar where you can wait inside at the bar? Is it Friday? Is the customer hungry? Are the patrons inside? That is, are the customers sitting inside? How expensive is the restaurant? Your goal would be to build a tree that would look something like this. Our end goal, this is where we're going. We want to have something that tells the restaurant, the first thing that people look at is whether there's patrons inside. Because when people go to a restaurant, if that restaurant is empty on a Friday night, they just don't go, they don't wait. They don't bother to go in. If that restaurant is too full and there's a lineup that goes around the block, then you probably also wouldn't wait. I don't know if you've ever watched, there's a beautiful Portlandia episode about the brunch place. Who's watched it? Okay. He's smiling. He did. But some people do love to wait for 1 hour at the restaurant. Just because it's so popular, it's where all the hipsters are and so on, and some people don't. So even when the restaurant is full, some people still wait. If the restaurant has people inside and the lineup is short, then everyone waits. Okay, and that's essentially, and then once you check whether there's people inside, if there's people inside, but the wait is over an hour, then it's likely that you're not going to wait. But if there's people inside, the restaurant is full, and the waiting time is only 10 minutes, it's likely that you will wait. Most people wait. And so you would reach this leaf. And so on. So this is what you would like to understand, is to have a tree that completely describes the behavior of individuals when they're confronted with the decision of waiting or not waiting in line. What can a restaurant do from their perspective? This is kind of a toy example, but what the restaurant could do is, well, they could just invite some people for free. They do happy hour at 6 o'clock to make sure that the restaurant always looks full when those 7 o'clockers start coming out for dinner. So if a restaurant knows what variables are important in order to attract customers, they can now manipulate. Okay, so now let's look at this variable. So the question though is, how do we build this tree? Why did I choose the variable patrons first? So let's examine the variable patrons. Okay, That's a variable that can take 3 values. And those 3 values correspond to some. That is, there are some people inside, and there are 6 cases of some. Oh wait, no, there are none. I did one too many. Okay, those are the ones in blue. In addition, we have in magenta 2 cases of none. Now, the one thing you will notice is for the customers that in the case when there was nobody inside, the decision was red. And that's why there are 2 red points here. Because those were the 2 customers who didn't wait because there was no one inside the restaurant. And then you have the customers corresponding to full, of which there are exactly 6 of them. Okay? And if you look at the green guys, this person didn't wait, this person waited, this person didn't wait, this person also didn't wait, neither did this one, but this person did decide to wait. And in effect, 2 people waited and 4 people didn't wait for when the variable patterns was set to full. Okay? So when you learn a tree, you are given this table. That's your training data. A person can stand outside a restaurant and can fill in that table. Type it into a spreadsheet on their iPhone. And then they just check whether the person, whether the custom waited or didn't wait. And so they enter green or red. So you build that, the restaurant builds that table. Once you've built this table, then you can choose any of these attributes, and the attributes being these columns, like patterns is an attribute, bar is an attribute, Friday is an attribute. So you choose these columns, and using these columns, you will construct a tree. Each of these attributes will be a node in the tree. And each of these attributes has a set of options. So for example, patterns breaks the data into 3 classes. So in this case, the tree is not binary like in the previous example, but there are 3 classes. Some variables like bar are binary, so you either have a bar inside or you don't have a bar inside. And some variables are have discrete ranges, like for example, the estimated wait time is either 0 to 10 or 30 to 60 or 0 to 10. So another thing that's very powerful about a decision tree is that you can have categorical data, you can have continuous data as the input, or you can have things that where there is an order, like the estimated time, or things where there isn't an order at all. For example, is it a French restaurant? Is it a Thai restaurant? Is it a burger joint? And so on. So you can throw in any type of data and you will be able to build this tree. And when you build this tree, the result of running one of these algorithms on building the tree essentially is this tree that I'm showing you here. And the trees are not unique because we will build them in a greedy fashion. Now, why do we build them in a greedy fashion? We do that to avoid a combinatorial explosion. If you had to consider all the possible trees that you could get with all your data, you would not be able to do it tractably. So instead, what we do is we first decide what the first node should be. So in our case, we need to decide which of these columns, that is, which of these attributes is the first one that we will use. When Stuart ran this algorithm, the machine decided that patterns was the first node that should be used. And then it decided that the second one was the weight estimate, and so on. Okay? So in order to learn a tree, the first big question we have to decide is which of the attributes to use first. If you have a data set, what is it best to use? Patterns or Friday, Saturday? Which variable will tell you the most about whether your customers will wait or not wait? Essentially, this question that we have here for two variables. I have two possible questions, and if you look at patterns, so we did the analysis in the graph, in the table. When we looked at patterns, we had none, some, or full, and that was the distribution of how those customers got split by that decision. However, if we look at food type, okay, so if we look at this alternate node, or decision variable or attribute, for that variable, there are precisely two of each kind. So if you are a French restaurant, one person waited, one person didn't wait. If you're Italian, the same situation. And so food type breaks into 4 categories, but the number of greens and the number of reds in each category is the same. So one of those 12 people waited for a French restaurant, and one of those 12 people didn't wait for a French restaurant. Okay, and then same for the Italian, and then 2 for Thai, and 2 for burger. Okay. So now the question is to you guys. Oh, actually, I put the answer there, so I can't do the question. So I was going to ask you, which one would you pick first if you were building a tree? Would you use the one on the left, or would you use the one on the right? And I unfortunately, when I was doing the PowerPoint slide, I included the answer at the bottom. So you would pick the one on the left, because the variable on the left is splitting. Your objective is to learn who waits and who doesn't wait. So if you use a node like the one on the right, it's not going to help you, because after you use that node, the number of people who wait and who don't wait in the children of the node is still the same. So you still haven't made a decision. You've just delayed the decision. You wasted computation to delay the decision, but you have not split. Whereas on the one on the left, I already know that if there is no one inside, people don't wait. If there's some people inside, people wait. And if it's full, most people don't wait.
So this can affect the depth of the tree that gets constructed?
That's correct. So if you don't want to build a tree that is wasteful, because then you're wasting resources, memory, computation.
Why do you need to decide about the first node? Why don't you just decide on a few and then fuse the outcome?
So you could just pick 2 nodes. Like I said, it's combinatorial. You could start with, say, 2 nodes. I mean, with 2, it's still tractable. But what I've argued is the way we want to build this tree is we want to build it in a greedy fashion to make the computation tractable. We want to choose which is the best node out of all the attributes, which is the best attribute to split the data. Once we've chosen that one, we need to choose the next one. And so we will build the tree top down, 1 node at a time. And by doing that, the algorithm is going to be extremely efficient. It's going to be really fast. Now, the problem with it is that the tree will have variance, because all you need to do is change one color of these points, and the tree structure changes. You end up with a very different tree. But that's where random forest will come in on Thursday. They will allow us to take all these trees, build a bunch of trees, and then we'll average that uncertainty. So for now, being greedy is not going to cost us much, because there's this other trick that is going to come on Thursday that will sort out the problem. Okay, and so in order to make this decision, we will use the concept of entropy. Okay? Because entropy is a measure of uncertainty, or likewise, or equivalently, a measure of information. The entropy of a binary variable, entropy is just p log p, the sum of a minus p log p. So essentially what we just need to look at, we have two classes. Suppose the total number of points is the number of positive plus the number of negative, and there are this many positive and there are this many negative. The entropy of this binary decision of you being positive or negative is just the number of the probability of positive times the log of the probability of positive minus the probability of negative, which is the number of negative divided by the number of negative plus positive, times the log of the probability of negative. Okay, so remember that the entropy of P, the entropy of a distribution pi is just equal to minus pi log pi. Okay, just like in your homework assignment. And so for a binary variable, there's only two outcomes. So the entropy, you would have, say, only two terms, the term for the positive and the term for the negative. If your variable was not binary, but say if it had three values, then you would have three terms. The number of points of one class, log the probability for that class, and then the second class, and then the third class. So three p log p terms. Once we have the formula for the entropy, we're pretty much done. So let A denote an attribute. So A is one of those columns in that table. And let's assume that that attribute can take k values. For example, patterns takes three values: none, some, or full. And let's say that that is dividing the training data, the whole space of training data, which is say E, into k classes, E1 to Ek. Then for each class, in order to compute, we compute this thing called the expected entropy. So the game we will play here is maximum expected utility. You don't know beforehand what's the probability that a point will end up in any of your children. So you need to compute the expectation. You know that when you split the data, there will be a certain entropy left in your children. And so what you do is you look, but you don't know how many points will end up in each leaf. But you can estimate it. You can estimate the probability. So we're going to do exactly expected utility, which is we're going to weight the utility, which in this case is information, is the utility measure. We're going to weight the utility of each of your children node. For example, for patterns, there are 3 children. We would take the expectation of those 3 utilities under the probabilities that they have. Okay? So P, if the total number of points is P plus n, so the number of positives, the number of negatives, then each leaf, the total number of points in leaf I, so these will be the points in child I, the points that ended up in the child divided by the points in the parent gives the probability of that child being reached. And then we look at the entropy of the child. So for example, the probability that you're actually I have the example after. Okay, just bear with me and I'll give you a numerical example. In addition, we're going to define a quantity called the information gain, or I apologize, that's been covered now. also known as the reduction in entropy. And so what we're going to look at is what is the entropy of a node, and then once that node is used, what would be the remaining entropy of the children. And essentially you want to see how much by making this decision did you reduce the entropy. Okay? If you've reduced the entropy a lot, you're doing well. If you haven't reduced the entropy, you're not doing too well. And essentially that's what we're going to use to pick which variable to use. We're going to apply the same calculation, which is this calculation here. Oops, sorry. We're going to apply this calculation here to each of your nodes. That is, to each of the columns in that spreadsheet, or equivalently to each of those attributes, we will compute this expected information gain. And then the one that has the highest information gain, that's the one we choose. If there's a tie, we just break ties randomly. Here's a numerical example for the two variables, patterns and type. So what I would do, okay, so first a definition, the entropy, so in that case we have 12 customers, 6 are green, 6 are red. So the entropy of the root node, we have 6 out of 12 red and 6 out of 12 green. So we're looking at the entropy of a binary variable that has probability a half. And the entropy for a binary variable looks like this. And where P is the probability of green. That entropy is higher at a half. And the unit that we use to measure it is bits. That's where the word bit, in fact, comes from, that we use routinely in computer science. Shannon defined it as the entropy of a fair flip at the point of the highest uncertainty. So that's 1 bit, the measure of entropy. And so we need now to compute the entropy of the parent minus the expected entropy of the children. And so the entropy of the parent is always 1, because you have an exact number of green and red in the pattern's case and in the type of cuisine. But now for the children, in this case, the probability, so we'll look at the cases. There are 3 cases. In this case, 2 out of 12 people go this way. 4 are, and that's for class red. Then for class green, 4 out of 12 people go this way. And for this other class, which has, so this one was red, this is green. So in this case, there are 2 green and 4 red. And so the probabilities are 2 out of 6 guys on this color and 4. Actually, I think there's, sorry, what am I saying? 6 out of 12 guys ended up in this leaf. Okay, so that's the probability that you're going to end up in this leaf here. It's 6 out of 12. This is the probability that you'll end up in this middle leaf. And this guy here is the probability that you'll end up here. And then for each of child, we compute the entropy of the child. Of course, we don't know when a new point comes in which leaf it will end up. And so but we do have estimates of the probabilities. And so essentially what we're doing is expected utility, where the utility in this case is entropy. And then we repeat the same procedure for here. And then we just look at these numbers. Which one has the highest information gain? And then not surprisingly, patterns has the highest information gain. Because when you split the data of patterns, you end up with decisions, you end up with groups that you actually have information for. So when you end up here in the class none, at that stage there's no uncertainty. I know that if you end up there, you're red. Whereas here, if I end up in any of the children, the probability that you're green or red is still a half. So it's the entropy is still very high. The entropy is still 1. And that's why when you subtract the entropy of the parents minus the entropy of children, you get 0 bits. Because you haven't gained anything by using that variable. And so that's how we build a tree. We take each of these guys individually, one by one, and we compute the entropy. And we compute the information gain. And then we just pick the one that has the information gain. We split the points at that stage, and then we repeat. We do this recursively. Okay, and then.
Is a bit the same as a log of 1/2?
This bit would be a half. It would be a half log a half plus a half log a half, so it's log a half. Yes. I'm just doing the entropy calculation in my head of p log p minus p log b minus 1 minus p log of 1 minus p.
I think it should be 0.541 instead of 0.0541.
Pardon?
It should be 0.541 instead of 0.0541.
Oh, I put one too many zeros. Yeah, I think last year that someone pointed a typo. So I think that's a typo. Thanks for correcting. Okay, so my advice is that this is the guys in 340. You all saw this in the final exam. Okay, this is a beautiful question to ask about trees because you can do this calculation by hand. So my advice to you is go home, do this calculation, make sure that it's clear. Thursday's lecture is how to use trees to build forests. If you haven't understood today's lecture, then there's no point in Thursday's lecture. So what I advise you is try to do this calculation, and if you're having trouble, come to the office hours so that we can help you. Okay, but the concept is quite easy. You pick one node at a time, you split the data, and you pick the node that has the highest information gain. Once you're done with that, you move to the next node, and you repeat the process. Okay. How do we do this for data that are continuous, like in R2? And here, by the way, I'm using a technical report by Antonio Cremonesi. So if you think your project will be about classification, then I strongly recommend you actually start reading that before Thursday so that you can fully get Thursday's lecture and have a good start into your project. I posted this in Google Group, the actual link to the paper. So it's in your email folder. Now, if we have points in 2D, so in this case, V is a point which has X and Y coordinates, it's a continuous point. What we can do in this case is we can choose the points and axis-aligned cuts to make the decisions. For example, I could just pick a point here and choose an axis-aligned decision. So that's my decision. I'm going to call theta. So that's my attribute. In this case, I haven't been given attributes. So I'm going to create attributes. And one possible way to create attributes is to look at the projections of the points in the x direction and in the y direction as the attributes. So this would be one attribute. Another attribute could be this line. Another attribute could be this line, and so on. And in fact, and the way it's described in Antonio's paper, what they do is I think they just pick a bunch of random axis-aligned attributes. So an axis-aligned because they're either vertical or horizontal. Now, if you do this, you can think of this as your first node in the tree. That first node splits into two classes. One class that is mostly blue and a little bit of green, and a class that is either yellow, green, or red. So we do this node 1. Then as we go down, and we go to node 2, for node 2 we might choose this decision that if it's to the right, if x1, so essentially the question here, if this value here is theta, the question is x1 greater than theta? If x1 is greater than theta, you send those points to the right. If it's less than theta, and theta is just a number like 0.7. If it's greater than 0.7 to the right, if it's less than 0.7 to the left. And if you keep following these decisions, as you can see, you might end up now with a leaf where most of the points are red. Okay? So in this case, we're not given a column of attributes, but what we can do is we can take a bunch of vertical lines. And in fact, there are several ways you could do it. One way people do is for each point, they place a line. Or they just pick a regular interval of lines. How you choose that, it doesn't matter. There's different implementations. But let's just say that you have a bunch of vertical lines, a bunch of horizontal lines. These are essentially your attributes. And then you take each of those lines and you check which one has the best information gain. And then you choose that one first. And then you move on to the next case. And that's essentially how this tree was built. And then when a new point comes in, you just apply those decisions to that point. So this point here comes in, you first check, is it above, let's say that this is 0.6. Is it above 0.6 or below? If it's above, you send it to the right. If it's below, you send it to the left. In this case, it goes right. And then you check, then it arrives at node 2. At node 2, you ask, is it to the left of theta or is it to the right of theta? Okay, it's to the left, so you send it left. And you keep making these decisions with the point as you pass the point further and further until the point arrives here. When the point arrives here, your answer is this histogram. Your answer is, okay, for that test point, it's most probable that it will be red, and the exact probability that it will be red is whatever the height of that red bar is. Okay, so we actually give you the probability of the point being of each class. Okay, so here's an illustration where we take of how entropy is used. We assume that I have a node Sj, and that node Sj can either is binary, and so you end up with the left children of Sj or the right children of Sj. And so essentially what we do is we compute the entropy of Sj and we subtract the expected entropy of the children. And this term here is just the probability of ending on the left or the probability of ending on the right. The sum is of the points that went left, the points that went right. So here is two cases. You can either use a horizontal split. If you use this split here, then you'll see that you'll end up on top. You have a few red, you have some blue, most of the yellow are there. If you, on the other hand, use this decision here, you see that you're splitting all the blues and greens to the left, and that's why the points on the left will have this histogram, and the yellows and reds here. So this seems to be a nice decision, and so the information gain here is 0.69, whereas the information here is only 0.4. So we go with this guy, and we don't go with this guy because we choose the guy that has the highest information gain. So, but we don't just consider two splits, we consider all possible splits, a large set of splits. The Microsoft actually just draws these splits at random. If you just pick a bunch of random splits in that range, you'll actually get pretty good results, especially when you do random forests.
If you have like more dimensions, could you do this like you do a dimensionality reduction, just by looking at the covariance?
Right. So you could do a dimensional reduction, but you wouldn't even need to. You could just pick You could be in 20,000 dimensions. So, but actually that brings another point, which I was planning to cover this on Thursday. Right here, I'm just choosing splits. But if I have 20,000 dimensional vectors, what I can do as well is I can first choose which dimensions to use, because dimensions are just attributes. So I will pick, say, 10 dimensions, and then for each of those 10 dimensions, I will consider 5 splits, and those will be my nodes. That's how I'll construct a tree. And when we do random forest, we will actually use this randomization.
Let's say you have some constraints. For example, you want exactly 4 clusters. How would you integrate it with the tree?
So right now we're saying that we want 4 classes. That's integrated. Because I'm saying my labels, this is a classification problem. So a cluster is a class. And in this case, the colored points there are training data. I actually know their label. So because I know the label, I know there are 4 classes.
But this will assure that in the read data after the training phase, you will also have 4 clusters.
That's correct. So the assumption here is you're classifying into 4 groups. And you know those groups in advance. You can use random forest for unsupervised learning, where you're trying to figure out what clusters when you're trying to do density estimation. That is covered in the report of CRIMN-EC later on. I'm not going to cover that in class, but you could use it that way. Okay, now this is why I asked you to do this calculation in the homework. I've been assuming that I have discrete classes, that I'm splitting the point into k classes, 4 in the previous example. But you could also use random forests for where instead of assuming discrete class probabilities, you actually use Gaussians to model the class probabilities. So you basically take the points that fall in a leaf, and if these are points in 2D, you could just compute the average and the variance, and so you fit the Gaussian to the points in the leaf. So like in this example here, when my decision is this vertical bar, I end up with these points on the right, and then what I do is I just fit a Gaussian to this point, and I fit another Gaussian to these points, resulting in this plot that I'm showing you here on the right. And then if I use a different split, these are the 2 Gaussians that I get. And in this case, the one at the bottom has higher information. Now, how do we measure higher information when you have Gaussians? We use the formula that you all proved in your homework. Okay? So if you use Gaussians, it's exactly the same procedure, except that instead of modeling the points as being of k classes, you're now modeling that there's sort of a distribution over the points.
Is this one unsupervised?
This one is still supervised, because here I'm saying you. I see what you're going on about. No, here you still would be supervised, but it's just you're just saying the label of the point. The label is not going to be red, green, blue. It's not going to be categorical, but the label of the point will actually be a continuous number. So in effect, rather instead of think of a supervised, think of this as regression, where you now want to evaluate the height, the probability of it being green. And this essentially is something that I've already gone over. Each split corresponds to a node, and each of these splits is parametrized. So basically the height, in this case, is the parameter. When a point comes in, that decision function decides whether the point goes left or whether it goes right. The way we make the decision is by maximizing the information gain. And then when you end up at the leaf node with a certain population of greens and blues and so on, like for example for this leaf here, most of the points are green, few points are blue, so we end up with a histogram that looks like this. So that's pretty much a summary of exactly how you do classification. I talked about axis aligned, and that's all I'm going to discuss in the course. But if you look at the report of Cremonesi, they discuss non-axis aligned. So, for example, this case, where you could use a bunch of lines just drawn at random without necessarily being axis aligned. Or instead of using lines, you could even use quadratics. Okay, so this sort of details of how you go about implementing these. And when you build trees, you actually make a lot of choices. And you could use Bayesian optimization to automate those choices. And in fact, some of my students, when they run trees, they actually optimize the tree automatically. They choose the max depth, with the type of decision that you use, how many dimensions you sample, etc. All those are parameters that you can tune automatically. As in the next lecture, when I talk about random forests, I'm going to go over all these decisions and how I'm going to basically show you plots showing how each of these decisions affects the data.